This video is about deriving the electric current from a number of parameters that make up a conductor and also make up a circuit. In order to get to this definition of current, we're going to progress in three major steps. The first one is to find an expression for the amount of charge moving through a conductor. The second one is to introduce the concept of drift velocity in the electric field. And thirdly, we're going to look at some current parameters, which include conductor geometry and also some material properties. For example, is it copper or is it another material? And from this definition, which we arrive at by the end of the video, it will be possible later to derive the concepts of voltage and also resistance, and then in the next step, the famous Ohm's law in a very simple way. My name is Andreas from The Fearless Engineer, and here we go. We have already seen that the electric current is defined as the amount of charges that move past the control spot within a conductor or conductive medium in a certain time instant. And this is illustrated in this idea of a cable, which you can see represented by this gray cylinder here. And inside the cylinder, we have charge carriers in motion, in this case electrons moving from left to right. And they are passing by this control station here, this red disk, and the red disk counts the number of charges passing by in a certain time t, and the electric current moving through this conductor, through this cable, is defined as the ratio of charges, number of elementary charges divided by the time t. The current is measured in amps, and the charge is measured in coulombs, and the time obviously is measured in seconds. That's our definition of the electric current based on charge and time. Now in the next step, we want to replace the charge Q by an alternate expression which takes account of the physical parameters of the cable through which the charges are flowing. This is what this slide is about. We want to find an expression that replaces the amount of charge in our very simple equation. And if you have seen the video or the practical example of the amount of free charges in a wire, which we computed a while ago, you might remember that we have already expressed the amount of charge Q as this equation here. If this seems unfamiliar to you, you might want to revisit this video, because there I explain in detail how we get to this equation. The general idea of this is to express the amount of charge moving through a conductor by a mixture of material parameters and also geometric parameters. The first one here is the elementary charge, E-. Then we have the geometric parameters of, for example, the cylindrical cable through which the charge carriers are moving. A is the cross-section area, L is its length. And this one here, this symbol, Ne-, this is the amount of free electrons in 1 cubic centimeters of conductor material. Now if we take this expression here, Q, and if we insert it into the definition of the electric current, we get this expression here, which is not anything more complicated than the previous one. We simply take the ratio of Q divided by T, insert this equation here in the numerator, and divide it by T. That's basically all we are doing on this slide here. And next we want to discuss the concept of drift velocity and the electric field and introduce these parameters into the equation which we have so far. And if we look at the equation we have derived up until now, it contains a very interesting ratio. It's the ratio between the length of the cable L and the time t it takes an electron to move from one side of the cable to the next one. If we take this ratio and replace it with a velocity, this velocity, it's what's called the drift velocity. We have made another video on the drift velocity, and you might want to revisit it to understand what's behind this concept. But the idea is we have a certain force acting on the electrons, and this force is pushing them along or pulling them at the same time even through the conductor by a certain speed, and this speed is called the velocity with which the electrons drift, the drift velocity. And we can replace the ratio of L and T by the drift velocity Vd, which brings us to this somewhat simplified expression here. And in the next step, in the second step on this slide, we can further elaborate on this concept and substitute the product of electron mobility and field strength to substitute the drift velocity in this equation here. We have already seen that the drift velocity depends on these two parameters, electron mobility, for example, in a copper conductor, and the field strength of the electric field permeating this conductor. And both parameters, they make up the drift velocity Vd, which brings us to this equation on the bottom here, which is the product between elementary charge, cross-section area A, number of electrons within a certain volume of the material through which the electrons are moving, electron mobility in this material, and the field strength. And the question might arise why we have to invest all this effort to get from this very simple definition of charge divided by T to this rather lengthy equation here. And the question is perfectly justified. Now let's look at the explanation why it's important to elaborate so deeply on this concept here. In the long run, where we want to get to is to a derivation of Ohm's law, the relationship between current and voltage and resistance. And this equation, which we have derived so far, sets us on our path to get there. What we are doing here now is we are assembling all the parameters into certain functional groups, the geometry group, the material group, and also the electric field. And we can now say that the electric current depends on the conductor geometry, only represented by the cross-sectional area, not the length of the conductor, interestingly, then its material properties, and also on the electric field. And if you have heard about Ohm's law before, the law states that current is the ratio between voltage and resistance. We can already glimpse this form in this equation here. If we say that the electric field, which is the reason why electrons move in the first place, this represents or is related to the voltage, and then the rest here, the geometry and material parameters, they are related to the resistance of a certain material. And this form here can be brought into a shape which leads us directly to Ohm's law, which is something we will investigate in the videos to come. For now, that's all. I hope you enjoyed the video. If you have any questions so far, don't hesitate to drop me a comment down below and I will get back to you. If you liked the video, leave a thumbs up and also think about subscribing to the channel if you like. I hope you have a nice day. See you next time here on The Fearless Engineer.